A standard 3D architectural model represents the permanent finished product. It details the structural integrity, MEP systems, and aesthetic envelope of a completed building. But a construction site is not a finished building. The actual risk exists in the dynamic execution phase. The lethal hazard is a temporal clash, a temporary power line and a crane radius physically intersecting in three-dimensional space for a brief, specific moment. Relying on two-dimensional blueprints to manage these moving, intersecting variables leaves a massive cognitive gap. Planners are forced to look at flat drawings and imagine how hundreds of concurrent activities will interact on the ground. When planners must mentally project 2D drawings into 3D space, the resulting interpretation errors correlate directly with on-site struck-by accidents and equipment collapses. Eighth-dimensional building information modeling, or 8D BIM, turns hazard prevention into a solvable equation. By plotting safety data directly into the three-dimensional space over time, hazards can be calculated and resolved before a single piece of steel is ordered. This predictive capability operates within a methodology known as Virtual Design and Construction, or VDC. The central rule of virtual design and construction is remarkably simple. We must build twice, first virtual, then real. Traditional safety programs rely heavily on retroactive checklists and physical site walks to catch violations. VDC shifts safety upstream, treating hazards as deterministic variables that can be engineered out of the process entirely. Achieving this requires three intersecting pillars: mapping the physical logistics, sequencing the timeline, and mobilizing data to the field. A rigorous safety model requires simulating the environment, the schedule, and the execution simultaneously. An architectural model alone offers no protection to a worker on day one. It lacks the actual geometry of the construction process. To calculate risk, planners must construct a digital replica of the execution environment itself, mapping every temporary element that enables the build. The site logistics model maps topography, adjacent structures, and access roads. Next, dynamic equipment like tower cranes are plotted with exact dimensions to calculate strict collapse zones. Modeling these volumes reveals bottlenecks, like an oversized vehicle clashing with an overhead structure. Resolving that bottleneck in the virtual model eliminates the need for a site manager to improvise a dangerous maneuver in the mud with heavy equipment. The logistics model defines the physical boundary layer, proving that space is a finite resource that must be actively managed to prevent accidents. Space, however, is only half the equation. Construction sites morph daily, rendering static logistics models obsolete within a week. Activating the fourth dimension, time, requires linking those 3D logistical elements directly to the project schedule, creating a timeline where objects appear and disappear precisely when they are scheduled to be built or dismantled. Deep excavation presents severe operational risks. Heavy machinery must operate with tight tolerances, navigating changing ground stability and limited access points. Earth-retaining structures are sequenced precisely, showing when piles and struts are installed. Officers scrub this 4D timeline to pinpoint narrow fall hazards. A physical safety barrier is then scheduled, appearing before earth removal to block the hazard before it materializes. 4D sequencing makes hazard prevention an actionable, scheduled event rather than a static geographic location. Mitigating a hazard on site is effective, but the primary principle of VDC is to remove the risk entirely. This is achieved through Design for Manufacturing and Assembly, or DFMA. Traditional construction relies heavily on raw materials being assembled in place. Pouring concrete at significant heights requires complex formwork, extensive scaffolding, and crews operating in high-risk zones. The alternative is prefabricated, pre-finished volumetric construction, or PPVC. Instead of hoisting loose rebar, the structure is fabricated as a unified module. BIM makes this possible by resolving complex geometric clashes and millimeter tolerances digitally, meaning components arrive on site designed to lock together immediately. By displacing the labor-intensive assembly to a controlled, ground-level manufacturing facility, the project strips out hundreds of hours of high-altitude work. Leveraging DFMA physically reduces the total volume of spatial clashes on the site, permanently lowering the baseline risk profile of the entire project. A flawless virtual rehearsal yields zero results if the sequence remains trapped on a desktop computer in the site trailer. The final technical hurdle is the BIM to field execution loop, mobilizing the spatial data directly into the hands of the frontline crews doing the work. Cloud-based field management platforms maintain absolute version control. When an engineer updates a clearance radius in the model, that data synchronizes across all mobile devices instantly. Foremen access the specific 4D timeline for their zone on a ruggedized tablet. They do not interpret a stack of 2D blueprints. They watch the precise assembly sequence they are expected to execute that day, complete with highlighted safety protocols. Physical QR codes posted on bare concrete columns link mobile devices directly to the virtual installation sequences for that specific room. This data integration overhauls the morning safety briefing. Instead of generalized warnings, site officers pull up the 4D model and demonstrate the exact spatial constraints the crews will encounter. The workers step onto the site, knowing where equipment will move, where temporary supports must go, and when collapse zones are active. Closing the BIM to field execution loop ensures that physical execution strictly obeys the parameters established during the virtual rehearsal. 8D BIM serves as the project's central operating system, embedding safety into the foundational data of the build. Safety is the calculated, natural output of rigorous site logistics, precise 4D sequencing, and integrated off-site manufacturing. The system relies on the continuous feedback loop. Quality inspectors use their field platforms to report deviations, ensuring the physical site constantly mirrors the approved virtual plan. This dashboard illustrates the system's effectiveness. By tracking key metrics like planned versus actual progress and BIM-supported safety briefings, managers quantify risk exposure. Monitoring these data points allow directors to systematically eliminate the deviation between what was virtually rehearsed and what is physically occurring. Model what to build, rehearse how to build it, mobilize that intelligence to the field. In a mature VDC ecosystem, a safe construction site is simply the accurate physical execution of its digital twin.